Good morning, everyone. So in the last class, we have discussed about the production graph, okay, and the different phases of the production and some different parameters on which this production history will depend, okay. This production graph will depend. So if I remember, in the last class, we have discussed up to the project development parameters. Can anybody confirm me? I think we have discussed up to the project development parameters, discussing about the well pattern and the well spacing and the well geometry. Is it right?
Yes, sir. Well
Yes, sir.
stimulation is the last topic.
Okay. So today we'll continue with this production parameters further. That earlier we have discussed the main parameters. So now we'll see if there is other additional parameters. Okay, that we have seen that there are different phases, different reservoir properties, different well conditions, different well designs. Okay, and then there comes some of the additional parameters. What are the additional parameters? The additional parameters may be the compressivity effect. As you can see that there may be some compressivity effect. Now compressivity of the gas or fluid, I hope you understand at this point. The compressivity means the volume expansion or reduction in case of gas or solid or liquid based on the pressure difference. Okay, so comparison to the fluid, comparison to the solid and liquid, for gas compressivity factor is very high. Okay, and then the initial adsorbed gas concentration condition, that means whenever you are going to produce the gas from the reservoir, it is absolutely important that how much gas is already stored there before you are going to start the production. Suppose consider to give you a crude example, consider a sponge. You know that a sponge is going to absorb the water. Okay, now depending on the condition, whether the sponge is totally dry, partially dry, or totally saturated with water, it will vary the capacity of taking the water with pressure at different pressure depending on the different condition of the sponge. Maybe it is a dry, maybe it is a partially dry, or maybe it is a totally saturated with the water. So obviously these three factors is going to depend about the water content or water to be captured by applying the pressure to the sponge. Okay, similarly in the reservoir pressure also, depending on the condition of the reservoir. Suppose the reservoir that maybe you know that the reservoir is trapped with the gas, mainly methane. That's why it is a coal bed methane reservoir. Now who is going to say or valid that okay, this at this temperature and pressure condition at this particular depth, whatever reservoir you are going to study, it is whether totally void of gas, partially saturated, or totally saturated with the gas? It is very difficult to say until unless you are going to do the laboratory testing. Okay, it is not very much easy. It is not very easy to say that okay, at this point the gases are totally saturated or the reservoir is totally saturated. That will be somehow that will be estimated from the desorption isotherm or the adsorption isotherm. Generally, it is the desorption isotherm. Sorry, it is the desorption isotherm for a particular reservoir. We will be seeing that in a later stage. So the compressivity effect of the gas, then the initial adsorbed gas concentration condition, okay, and there are hydrodynamic effects. Hydrodynamic effect means the water change influences. Okay, now before we are going to discuss these three, let me discuss you some of the figures they have given from the field studies. Please check the figure 3.9, 3.10 and 3.11 serially. First 3.9, you can see that here they have given the gas production rate with time in the x-axis, and the y-axis there's a gas production rate, and they are varying this gas production rate based on the drainage area. What is your drainage area? Drainage area means the total area you are going to collect the water from where. Okay, so in the underground if your drainage area is going to increase. Okay, if your drainage area is going to increase, so what it is supposed to give the impact? As your area is going to impact, you have seen earlier that whatever the normal production graph is lying, there are three phases. This is the three phases. So first, a constant water rate and very few amount of the gas we produce, then quickly descending about the water stage, and the gas production rate is going to reach at the peak stage at the end of the phase 2, and then finally at the end, at the gas at the phase 3 condition, the gas production and the water production are going to be reduced very quickly, whereas or more or less flatter, uh, and then the gas production is much higher than the very higher than the water production. And at this point you can say that there is a very little or no water present in the coal bed methane reservoir. Okay, so this is a typical graph, okay, a general graph. Now if you now whatever water production is coming, obviously the water production is coming based on the connectivity of the open channels, which is called the permeability, the cleavage surfaces or the cleat surfaces, how they are going to connect with one another, the apertures, how they are going to orient themselves, that is going to dictate about how much water you are going to take out from the coal bed methane reservoir. Suppose that this network is going to be spreaded by 1 kilometer by 1 kilometer, suppose, then obviously if there is a interconnectivity of the open fractures, okay, so obviously within this area whatever water is present, that will be taken out to the surface by pumper, by running the pump. Okay, if that area is going to be reduced, suppose it is 500 meter by 500 meter, so obviously whatever water is going to produce, that will be much less than other. So increase of the drainage area is obviously going to increase the total water production. So the same thing is going to be discussed here. If you see the graph figure 3.9, you see the title is the sensitivity of the gas production rate to well drainage area. That means with the variation of the well drainage area, how the gas production rate will is going to vary. Why this? You can see that they have taken three conditions: 40, 80 and 160 acre drainage area of that CBM reservoir. So what is happening whenever the drainage area is much less? So obviously you know that the first water will come out and then only the gas will come out. Okay, now as you are going to increase the area, certainly the total water that is coming out, that is also going to increase. So until, and you know that until unless the water is going to be produced, the gas fraction is going to be very much less. So in that case, what will happen, that when you are going to change the drainage area from 40 to 80 to 160, your water production rate is going to increase, and so with time the gas production rate is going to be shifted at the right side. That means the gas production rate will be much more delayed because the water production rate is much higher, or the water production, total water production content is very high because the drainage area is becoming higher. And then accordingly, when the water is going to reduce, you will see that the relative permeability phase will begin, and so it will gradually increase, the gas production rate will increase, and then finally it is going to decrease. Again, one point to be noted, that as the drainage area increases, the possibility of gas production is also increases. Okay, so that's why you can see that after prolonged time the gas production is much higher from the higher drainage area, whereas you can see, you can confuse about the fact that the peak is going to be reduced somewhat a little when the drainage area is going to increase. Why? Again, this is related to the gas production and the water production comparative. Okay, this is in comparison, in mixing of the gas production and the water compression, and so the relative permeability is also coming into the play. So when the water is very high, water content is very high, obviously the relative permeability of the gas will be very much less. That's why when the water content is very less, the the chances of the relative permeability of the gas is becoming much more higher, and so the peak production is a little bit higher in the smaller drainage area than the higher drainage area. Okay. Now I request you all to ask question if you are having any doubt. Okay. Otherwise you may feel trouble in the later stage. Okay. Now let us come to the second figure, figure 3.10. What this is going to dictate? This is going to dictate about this is going to show us the sensitivity of the gas production rate to the permeability. Now this is very easy to understand because you already know that the permeability is going to be dominated by the orientation and the presence of the natural structures, and so whatever the gas production rate is coming out, okay, whatever the gas production rate is coming out, that is obviously how much permeability of the reservoir is. That is going to depend on the how much good permeable a reservoir is, and so as you can see, the permeability, which is the unit, is millidarcy. Okay, unit of the permeability is the millidarcy after the name of the scientific Darcy, who has given the concept of the permeability or the Darcy flow. So as you can see, the permeability is increasing from 10 to 20 to 30. So what is happening? The permeability is nothing but the Q, okay, quantity flowing through some section, okay, in presence of the fluid viscosity and in the presence of the pressure gradient. So that Q is going to increase. So water quantity per second, because the viscosity obviously is going to constant because it is the same water or the gas. Okay, it is the gas production rate, so the gas, and then the pressure is going to change. Why the pressure is going to change? Because you know that the permeability is very much pressure dependent process. So if you can see that if you are going to connect, you understand the mining. Okay, suppose you are going to take only one gallery, okay, or one heading. A gallery is having both way accessible, but a heading is only one way accessible. Okay, so suppose you are considering only one gallery, so the pressure difference between point 1 and point 2, okay, air will flow from high flow zone to the low flow zone. Okay, so depending on this pressure variation, the air will flow. But if there is any suppose there is a junction point and four galleries are meeting there, okay, it is a four junction point, so it is a plus sign. Imagine that it is a plus sign of gallery. One depressed gallery and one level gallery are going to meet at a center point, which is called a gallery junction. And then if you are going to take the point, if you are going to check about the pressure point, obviously that is going to be much more pressure reduction due to the other galleries available. So at the same point, okay, whenever there is a other connectivity is present, so obviously gases or the fluid is going to flow in the other directions also, so that's why it is going to increase the permeability, and so the pressure is going to reduce. And so for the low permeability case, which is dominated by the low pressure gradient, the graph is very much less. So you can see that the gas production rate is going to be reduced somewhat, and then it is going to increase, but the peak gas production rate is very less, and then it is going to stabilize and going to flat with increasing time. Similarly, if you are going to if you are going to increase the permeability, what is going to happen? The gas production rate is very few. In the second case, as 20 millidarcy case, you can see that it is going to increase a little bit, and then it is going to again reduce, and then again it is going to increase. Okay. And in the third case, when your permeability is 30 millidarcy, very high, so you can see that it is going to increase from the very first stage, and it is going to reach the peak. Peak gas production rate is approximately near 150, which is the generally 3 times higher. So if I take the lowest gas production rate is the 50, so this is approximately 3 times higher. So you can understand that how the gas production rate is going to change. Okay, now whenever you are going to see the production, you have to think from the permeability point of view, because permeability is very much going to affect your gas production. The third graph, 311, it is going to show us about the sensitivity of the gas production rate to the hydraulic fracturing. Okay, hydraulic fracturing half length. Now, half length or the full length is the length of the fracture. All of you know at this point what is hydraulic fracturing process or the method and why it is used. The concept of the hydraulic fracturing is clear to all of you.
Yes, sir.
Okay. So as you know that hydraulic fracturing process, okay, it is going to be measured in the underground borehole, okay, and so obviously again this is a fresh fracture which is going to be created by the water, okay, and you have to ensure there are certain assumptions. I'm not going into the detail, and you have to ensure that you are going to create a fresh fracture, which is very difficult in the underground, because in the underground the rock is not an intact rock, it is a rock mass. Okay, now with this graph, as you can see, with time, okay, x-axis they have put the time in days, and y-axis for all the cases they have put million standard cubic feet per day. Okay, so in this case you can see that as the fracture half length in feet is going to increase, so what is fracture length? Fracture length means it is going to give the extent or the persistency, okay, or how much length the fracture continues. Okay, so if the length is going to increase, so obviously your flow is going to increase. It may happen that at the smaller length the fracture are not going to intercept one another, so a fluid that may or the gas that may migrate from this place to 100 meter or 50 meter away from this, but until and unless it is going to be intercepted by other fractures, it cannot escape to the atmosphere or the surface. If it is just mutually exclusive, that means there is only one fracture present, no other interrelation with any other fracture, so obviously the gas can migrate based on the pressure from one higher datum point to the lower datum point, okay, depending on the pressure head or the connecting head or so on. Okay, the Bernoulli's equation will come place, you know about that, so I'm not going to discuss, but it is trapped there, it is trapped there with some pressure. But if it is going to be connected, if the fracture length is going to increase, suppose it is going to increase, suppose 500 meter or suppose 600 meter, and at that point it may have the chances to intercept with other fractures. So what will happen? So obviously it is going to migrate from one place to another place, and again whenever the fracture length is going to increase, you know that whenever you are going to move from away from the source, your pressure loss is increasing. That is the principle is coming from the fluid mechanics. Okay, so as you move away from the source, your pressure is going to decrease, so the pressure gradient is also going to decrease. So obviously you can see that your with the days, as it is going to move, as the length is going to increase, as you are going from the left side to the right side, that means length is going to increase, so obviously your production is going to reduce. But obviously the more is the fracture length, is obviously the more is the gas production possibility. Okay, so these three are just from the results of the field studies that they have given, so that you can understand how the production is going to vary other than the parameters discussed earlier. Okay, so when you are going to read, when you are going to answer about the question that what are the parameters that are going to be governed for them, that are going to dictate the production, so you need to read it from the text also, and as you have understood the graph, you may include some of the parameters as it is given from the graph also. Okay, to complete your answer. Now let us come to the additional discussions, additional parameters. Okay, so additional parameter, they have first mentioned about the compressibility effect. Okay, compressibility of the coal is extremely high as compared to the conventional gas solid reservoir. Okay, because compressibility means if you are going to apply the pressure or the force, it is going to compress, and if you are removing the pressure, it is going to expand. So coal is also, depending in comparison to the other type of rocks, coal is also very much compressible. Okay, as you can see that the pore volume compressivity of the coal. Pore volume compressivity means pore volume, you understand. So the compressivity value, whatever has been given, that is related to the pore volume inside the coal matrix, not the total solid coal outside. Okay, it is the inside of the pore volume compressivity. That means if you are going to apply the pressure or apply under the stress, the pore volume is going to change like this fashion. Okay, per psi pressure, it is going to change like this. But then obviously if the pore is going to be filled with the water, or it is filled with the gas, or both, it is becoming a fluid, then obviously again with the coal compressivity, the gas compressivity and the water compressivity will come into the effect. Okay, now as the all the cases, the CBM reservoir is not totally saturated, obviously, because if it is not totally saturated, because there is a it is supposed that the total fracture network is present, their presence, their orientation is so high, okay, they are so interconnected that obviously it will not be 100% saturation. It may be 50% or 60%, because some of the water is obviously going to come to the surface, or some of the gases are going to be escaped into the surface. Some of the water may be going to the other downside area when they are going to connect with one another. Okay, so in some cases it is observed that it is never 100% saturated with the gas, a coal methane reservoir. Okay, so this is the case. So as you can understand that depending on this pore volume compressivity, the pore volume accessible to the gases will be also increasing or decreasing. If it is going to compress to lower volume, then the available space for going to be which is going to be absorbed by the gas is also very much less. So obviously your gas production, or obviously your gas storage capacity may change. This is the fact they are going to discuss here. Okay, the next point is the initial gas concentration. Okay, the initial gas concentration is also very important. Why? So this can be, you can see that line I have underlined is the initial gas concentration in a coal. C may not be equal to the amount of the gas that can be absorbed into the surface of the coal. Okay, you have to understand this first. Suppose the at some 500-meter depth, the pressure available is 1.5 megapascal. Suppose, okay, 1.5 megapascal or 1500 kilopascal. Okay, but if at this pressure, at that depth, at suppose 14 degrees centigrade in the underground, because there is geothermal gradient, at this temperature and pressure condition and that particular depth, if the total reservoir is saturated with gas or methane, then only I can say that the reservoir is totally saturated at this point with this temperature pressure condition. Okay, but then as I have mentioned that it is never possible, it is not I, the researchers are telling that it is never possible that the reservoir is totally saturated. How to get the idea that at this particular pressure the reservoir will be having this type of gas? That is only available by the gas isotherm concept. In this figure you can see this is the desorption isotherm, okay, which is estimated from the field desorption canister test, okay. And so whenever you will see this type of graph, okay, you can very well understand that with the pressure how much gas content is possible for this particular reservoir at this particular temperature and the pressure. The temperature, because it is isotherm, okay, at particular temperature, constant temperature. And as you are going to increase the pressure, the graph is showing you the total capacity, okay. This is established from the desorption canister testing in the field, or taking out the coal sample from the CBM reservoir. Whereas I will show you later in the laboratory example also, in the laboratory also, you can get this type of graph by taking study on the injecting gas in the total coal sample, in the coal sample. That process we will be discussing after we have discussed all those parameters. Okay, I'll show you the method. I'll show you some of the articles so that you can understand. But for the time being, you just understand that this is the graph we need to study. So this fine line is the disruption isotherm graph, which is going to relate at what pressure at this particular temperature the gas content is being present in SCF per ton, standard cubic feet per ton. Standard cubic feet means 15.5 degree centigrade temperature and atmospheric pressure. Okay, 101.3 kilopascal. Okay, so now you can see that depending on the nature of the graph, you can see that it can be present in the initial run with the initial pressure. Okay, initial condition, it is going to be very much increase very quickly. Okay, it is going to increase very quickly, but as the pressure is increasing much more, suppose in this case beyond 400, you can see that it is going to a little bit flatter. Okay, so whatever concept or whatever the pressure you are going to see here, so you can understand that obviously in the initial stage the gas content or the gases are coming out, gases are absorbed. As it is desorption, so you have to start from the this point, because it is desorption. If it is adsorption, you can start it from here. So the nature, I am just discussing the nature of the graph. At the initial, from the 0 to very small pressure range, you can see that the gas content is very high. It is showing the very steeply increasing, approximately 45 degree or 60 degree steep. But then with higher pressure, it is showing the much more flatter. Why? The concept is that in a coal or in a porous media may be in a coal in sandstone, which are comprising of the pores, micropore, mesopore, and the macropore. It is called the porous media. Okay, so whenever you are going to take a lump of the coal, you can estimate in the laboratory what is the pore volume. Okay, so now if you have estimated the pore volume, then you can readily know that this pore volume is being distributed by the micropore, macropore, and the mesopore. And so whatever gases are going to be present into this in an adsorbed state is also the total pore volume is fixed. Pore volume is never going to increase or decrease. Okay, theoretically. Okay, because for a particular type of coal it is fixed. Whereas applying the pressure, coal can be expanded or contracted, and that's why its total volume is going to decrease or increase. In that aspect, its pore volume is going to reduce or increase, but never a pore volume inside the coal is going to change. Okay, that means you are not going to add, suppose you are going to measure the same coal and you are getting that, okay, 0.5% porosity or maybe 2% porosity. It is not the case that after some time, if you are not doing anything, you will find that it is going to increase in the volume and it is showing 5% porosity. No, until unless you are going to change its structure, it is going to absorb the gas, or it is under any chemical condition, its porosity is a physical property. It is not going to change. That's like the density. Okay. Now, as you can see that in the initial stages, let me explain you the graph. I'll explain you. There is another graph like this when we are going to dictate the recovery factor, okay, which is this graph. Let me show you. This graph is also very important. This figure 3.14. This is also very much important. In detail also you will be able to understand this. But for the time being, let me mention this, that whenever you are going to adsorb the gas, okay, as you know that in the initial stage, there is a total pore volume is accessible. So the moment you are going to put some gas into the coal, okay, you are going to inject some gas into the coal, what will happen? Its total pore volume is accessible to the earlier molecules to the molecules of the gas. So what will happen? Suppose there is 100 pores are available, and you have given only 20 pores of the molecule, 20 gas molecules. So what will happen? This 20 gas molecule can take any of the 20 molecules, 20 pore from this 100 pores. So then after the end of this, all 20 are absorbed, and then remaining are only 80 pores. In the second case, again you are going to increase the pressure, and suppose you are going to increase, you are going to inject either 20 or 25, suppose. Then what will happen? Again they are going to take another 20 or 25. So remaining after the second stage, the total pores available will be 60 or 55. So if you consider the with stages, what is happening to the accessible pore volume? It is going to decrease from 100 to 80 to 60 or 55. That means the total accessible pore volumes with each stage is going to reduce. Okay, the total pore volume that is accessible for absorption of gas, okay, that is going to reduce because some of the pore volume is already occupied by the gases which is sent earlier. So what will happen? Obviously, whatever gas has been stored earlier, it will not be in the same rate, it will not be in the same fashion with pressure. So that's why the slope is going to decrease now. So you can see that with higher pressure, as the accessible pore volumes are going to reduce, the gas isotherm, the disruption isotherm is going to reduce, and at the final stage, it is becoming more or less flatter. More or less flatter. It is already somewhat increasing because of the fact that at this particular reservoir pressure, whatever gas saturation is possible, that is going to be dictated. Suppose you can see that if I take this last corner, suppose it is going to give you 1500 psi. Okay, so at 1500 psi at this point, you are going to get approximately 430 or 425 SCA per ton gas content. That is for that particular type of coal. Here, as it is for the reservoir, so this is for particular type of reservoir. Okay, so you can see once you have taken this graph, now you can establish, now any coal sample you are going to take out from the reservoir, okay, from that particular reservoir, you have a less idea, you have some idea that okay, this is the disruption graph of that reservoir. So any coal should lie on, any coal isotherm you are going to test should lie onto this graph. It should be matching. If it may not be actually matching, but it more or less should be showing the same trend. Now come the twisting. Here you can see that the initial is given as 300 SCF per ton. What does it mean? That means they have taken out some coal sample, and they have tested, and they have measured that it is only having 300 SCF per ton. Okay, a coal sample. But the isotherm, the disruption isotherm is showing this graph. So suppose at this 1200 psi, it is showing only 300 SCA per ton, whereas as per the disruption isotherm graph, it should be showing approximately 400 or somewhat greater than this, but it is showing somewhat lesser than this. That means, what does it mean? That means its maximum capacity was 400, but it is showing only 300. That means 100 SCA per ton is the gap. What does it mean by the gap? That means it is only saturated by the 75% of the saturation. The reservoir is saturated only 75% of the gas at this particular temperature pressure condition, because other 25% of the pore gas is not available. So the pores are available, but the gases are not filled up. Okay, the pores are available because the coal pores are obviously there, but the gases are not available. If the gases are available, so the initial gas content should have lied onto this disruption action graph. This is the dilemma of the coal bed methane reservoir, and you can only know about this by 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 taking the desorption process. You cannot know, you cannot estimate that whether a reservoir is saturated or not. Now suppose this is the desorption graph, okay, and you are taking out some coal and you are going to do the desorption graph. So what will happen? You have put it into the core. Suppose at this stage at 1200 psi it is showing 300 SCF per ton and it is supposed to show 400, approximately 400 or more than that. So if you are going to reduce the pressure from 1200 to 1000 and so on, okay, 800, 600 and so it will follow the same path. It should follow the same path, but you will not get any production. Why? Because it will give rise the production only when the reservoir pressure is going to be reduced from the gas pressure. Okay, if you are going to reduce the pressure from this point to this point, what is happening? You have reduced the reservoir pressure, but the gases are not present. Na? At this stage, there is a gap. This is the gap. Gases are not present. Gases are not totally saturated. Okay, the reservoir is not totally saturated with the methane. Gases are present only 300, so it will follow this path. This is the pressure. So what will happen? From this 400 to 300 pressure, okay, this zone, suppose this 1200 to 400 pressure, because this line is coming to the 400 where it is going to intercept the initial gas content. Okay, up to this point, if you are going to reduce the pressure, gases will not come out. If we are going to reduce the pressure from 1200 psi to the 400 psi or somewhat that, you will never get a gas. Why? Because water will only come out, because the gas will not come out, because it was not totally saturated at the 400 pressure, at the 400 at this 1200 psi pressure. This is the 1200 psi pressure. It is showing the gas content like this, but as per the isotherm graph, it should be shown that its gas content should be like this. This is the gap, that means it is not saturated totally. So as you going to decrease the gas amount, okay, you are going to, as you are going to reduce the pressure, the gas content should be following the same path. The moment when the reservoir gas content is matching with the initial gas content, it is the limiting condition. The point where the reservoir gas pressure or the reservoir gas content is same as the initial gas content, okay, you are in the limiting condition. The moment below, if this is, suppose this is 410 psi, the moment you are going to reduce your pressure lower than 410 psi, suppose you are going to give 400 psi, what will happen? Now the initial gas content, the initial gas content pressure is going to reduce. Why? Because this graph is showing that the pressure should be reduced. So as the pressure will be reduced, now the reservoir pressure is going to reduce then the initial gas concentration pressure. So what will happen? Gas particles will be dissolving from the pores, and now you are going to get the gas production. Okay, this point where the initial gas content is going to superimpose with the desorption isotherm graph, on the desorption isotherm graph, this point is called the critical desorption pressure. This point is called the critical desorption pressure. It is defined as the pressure beyond which actually the gas production will start. Okay, if the reservoir pressure is much higher than the gas production pressure, than the critical desorption pressure, you will not get any gas production. Okay, and this gas desorption pressure is particularly for a particular reservoir. If you are going to change this initial gas content, suppose this initial gas content is being changed from 300 SCF per ton to 350, then it should lie here. Okay, and accordingly it will going to, if you increase this at the constant gas content, initial reservoir gas content, if you draw a line here, it will try to intercept this. So with this line, when you are going to draw the intercept on the x-axis, you will get that the initial gas desorption pressure is going to increase, maybe around 600 or maybe around 700 or 800. So in that case, this is the only idea which is possible, that if reducing the pressure from a reservoir, you are going to get the gas production at the same point of time when you are going to get the water production, then only you can understand that your reservoir is totally saturated with the gas. I repeat again, if by reduction of the pressure or reducing the pressure by taking out the water, you are going to get some gas production in your production well, you are going to get some gas quantity, then only you can say that your reservoir is saturated, was totally saturated with the gas. If not, if you are not going to get any gas, then obviously the initial gas content is lying much below than which is supposed to be given by the desorption isotherm graph, like this. This is the supposed to, this gas content is supposed to be 420 or much more than that, but initially the gas content is given as 300. So from 420 to 300 it is undersaturated. Okay, and so if you increase the pressure at this point, if you increase the pressure, it can absorb much more gases. Okay, so the point is going to vary in the higher direction, so you are going to get this part of the graph. Okay, and this point where you are going to, which will give you the idea about when the production will start, gas production will start, this point is called the critical gas diffusion pressure, which is given by this point. Okay, and then if you further below the pressure, you will get both the water and the gas production, and you will get much more higher gas production in this area. But again, let me remind you, you cannot remove the total amount of the gas, you cannot put the reservoir pressure in zero, never, because there are certain amount of the water you cannot take out. You must have heard about the mobile porosity and the immobile fluid porosity. You must have heard about the connate water. Anybody, can you correlate? You know about the mobile fluid saturation, immobile fluid saturation, or the connate water?
No, sir.
Okay, then let me tell you. The mobile fluid saturity means, the mobile fluid saturity or the mobile fluid saturation means the pore volume is filled with some fluid which is mobile. That means if you are taking out the pressure, the fluid can be transferred from one place to another place, or it can be taken out. That is called the mobile fluid saturation. In comparison to that, there are immobile fluid saturation. That means some amount of the fluid which is stored into pore spaces you cannot remove. You cannot remove. This is called the connate water, CONNATE, connate water, or the immobile water. Okay, and so in some cases the pore volume is not at all having totally free from the, or totally void. Sometimes it is filled with the water or any other fluid. Okay, in case of moisture also, there are also mobile moisture, there are also immobile moisture. Okay, suppose if you are going to take a coal from some depth, okay, so depending on the reservoir condition, that coal block should be having some amount of the moisture. But if you are not wrapping with the bubble wrapper, the moment you are going to taking out the surface, its moisture will vanish. Why? Because you are going to reduce the pressure. At the reservoir pressure, it is having gamma H. So based on the stress, based on the depth, it is already having some pressure acting on it. Okay. If you are not pouring that, the whatever moisture is available inside the coal, the moment you are going to take it out in the surface, its pressure is released, so it will be vaporized and the temperature will increase. Okay, because it is sunlight will come, or it will be totally escaped into the atmosphere. So that's why whenever you are going to collect the coal sample, you have to take the coal sample at that point and you have to wrap it up so as to preserve the moisture, so as to preserve the reservoir moisture. That means if the coal is, you are going to test about the moisture content, taking some of the coal from there, and you are going to find that it is having 5% moisture. So then you can understand that at that level, at that depth, at that working point, with that temperature and the pressure effect at that depth, the coal seam is having this percent of the moisture. Okay, you have to take out, and if you are going to report this, it will be reported as a as received moisture. Now, suppose if you are going to prepare the dry sample, okay, so you are going to put by the standard process, there are standard process, and you are going to prepare the dry sample from that coal. And then you are going to test the sample. You will find that in the dry sample also there are 1.5% of the moisture available. The sample is not totally dry. So what does it mean? From 5% to 3.5, 5% to 1.5%. This 3.5% of the moisture was the mobile moisture. Okay, but this 1.5% moisture, as you have dried up the sample under 110 degrees centigrade for consecutive 2 days, okay, this is the standard process in the closed chamber. But even if you have to dry the sample with the constant weight, but even if you will dry, you will never see that the moisture is 0%. Okay, if the moisture is 0% available, that means it is also dictating by the coal structure. Okay, but some of the coal you will see that moisture is still some remaining. That moisture is called the immobile moisture, which cannot be taken out, or which is called the connate water, due to the connate water. Some of the water is always lying with the coal, that you cannot taken out. Okay, that is called the connate water. So depending on the saturation, the immobile fluid saturation, the mobile fluid saturation, then again there is a gas saturation, there is a oil saturation, or there will be water saturation, or there will be fluid saturation. So now you can see some of the ideas that a pore volume can be filled with any one of these individually, or a amalgamation of two or three: gas, water, or fluid, or some chemical fluid. Okay, so in all these cases, the saturation is going to dictate how much free space is available for the gas only, and so obviously it is going to dictate the gas content. Is it okay to all to understand this graph?
Yes, sir.
Okay, so this is the graph which is going to give you the idea about the other compressibility and the initial gas concentration. So this is the initial gas concentration. The third point which they are going to discuss is the hydrodynamic concentration. Now the hydrodynamic concentration means, you know, hydro means water. So whenever you are going to take out the water, how the reservoir will behave? The reservoir will behave, obviously its relative permeability is going to dictate. Okay, so you can see this is the permeability closure. Okay, see the effect of the permeability. As you are going to take out the pressure, what is happening? You know that whenever you are taking out the pressure, the water you are going to take out, if the pore spaces are filled with the water will be also coming out from the pore spaces, because water is not adsorbed. Water is remaining there in the action of the pressure. Okay, gases are adsorbed. Okay, and sometimes, okay, sometimes also at some point of time the water also can be stored, but here we are discussing that only gases are adsorbed. Water is just adsorbed, water is just accumulated there depending on the pressure, depending on the permeability. So if you are going to take out the water, what will happen? The moment you are going to take out the water, you know the pore volume, you know the effective stress principle. Effective stress is the normal stress minus the pore pressure, or the pore pressure what is available, or the water pressure, and which is has to be reduced. The pore pressure has to be reduced for the effective stress principle from the normal stress component only, but not from the shear stress component. Okay, okay. So if you are going to take out the pore pressure, what is happening? Effective stress is equal to vertical stress minus the, on the normal stress minus the pore pressure. If you are going to take out the pore pressure is becoming zero. Then whatever is the effective stress is becoming, it is going to be same as the vertical stress. That means the stresses are going to increase. If the stresses are going to increase, what is happening to the coal surface? The coal is experiencing much more stress. At the same point, because you are going to take out the water. So what will happen? Consider the natural fractures, consider the apertures, consider the pressure. Okay, you are going to apply the pressure because the stresses are applicable, stresses are increasing. So what will happen? The apertures will try to close. The two surfaces of the same discontinuity will try to close, will try to come one another, towards one another, and so it will reduce the permeability. And so you can see that as you are going to take out the pressure, this is called the closure pressure. Why it is called the closure pressure? Because you are going to take out the water much and much more and more, and so you are going to reduce the permeability, and so the gases will also come out, and you are going to totally shut out shut in sorry it will you will totally going to shut out the coal, shut out the borehole. That means there's such no such water will can go and reach the fill the hole borehole. Okay, so as you are going to take out the pressure, okay, the permeability is going to reduce. So what will be the effect? If the permeability is going to reduce, you have seen what is the effect. So if your permeability is going to reduce, see the gas production is going to decrease. So your gas output will be also going to decrease. Okay. So these are the some additional consideration, okay, which you need to know about the gas production. Now, I request you to all to be very careful about this isotherm study and this production theory. For this, the results are going to just help you, but you have to understand about the theory in a clear way. Okay. And anybody is having any discussion, any confusion, you can note it down. If it is not possible in any class, you can always communicate to me in the next class so that we can discuss for all people. Okay. So I'll stop you here. Next class, we'll start with the acquiring and integrating the reservoir data. Okay. Any questions for today?
सर ये आपने आज कहा ना कि पोर प्रेशर को हम जब पानी निकालते हैं तो पोर प्रेशर कम होता है तो
Yes.
प्रेशर इफेक्टिव इंक्रीज होगा तो
Pore
एडजॉर्ब
pressure?
होगी गैस या डिसॉर्ब होगी पोर इफेक्टिव पोर प्रेशर सेम पॉइंट पे प्रेशर इंक्रीज होगा ना
Effective stress is going to increase. Pore pressure, if you are going to take out the pore, if you are going to take out the water, the pore pressure, because pore is filled with the water, so water pressure is, you are going to take out the water, so pore pressure is going to reduce. So whatever the surrounding stresses are there, earlier your surrounding pressure was much higher, but your inside the pore was also the surrounding pressure was much higher. So whatever the surrounding stresses are there, earlier your surrounding pressure was much higher, but your inside the pore was also the surrounding pressure was much higher. And that's why its permeability is going to reduce. Okay, so from the earlier condition. So when you are going to increase the stress, obviously it is trying to close the natural fractures, and that's why it is going to reduce the permeability. Is it okay now?
सर आपकी आवाज ही नहीं आ रही थी अभी नेटवर्क इशू
Acha,
था सर
okay,
आपकी वजह से
okay. So now you can hear me properly. What I am trying to say, that whenever you are going to have a vertical stress, you are having a pore pressure. Okay, whenever you are having a pore pressure, the vertical stress minus the pore pressure is the effective stress. But when you are going to take out the water, your pore pressure is going to reduce. Okay, so whatever is your effective stress is going to same, or is it is going to same as the vertical stress. So now your effective stress is increased than the earlier condition, and so the coal is experiencing higher effective stress. So at this higher effective stress, the apertures will try to close, okay, or the open fractures will try to close because the surrounding pressure, the surrounding stress is much higher, and that's why its permeability is going to reduce. Okay, is it okay to understand now?
यस सर यस सर
Okay, any other questions? Okay, then I'll leave you. Okay, thank you. And I have already taken your attendance, so please try to be present in the class within first 15 minutes. Okay, it is not the case that I'll be always checking at the last moment all the participants, and the participants will be present only in the after some classes has already started. Okay, thank you. Have a nice day.